Hello students and welcome to the quick solution of All India Cast Test Series JEE Advanced 2019 Test 1A Paper 2 Code ENF Physics. Let's move to question number 1. In question number 1, consider the two blocks with friction coefficient and mass as shown. If the value of frictional force F is equal to 10 Newton, then we have to check the validity of these statements. Let we have assumed this complete system is moving on this horizontal surface. In that case, if I draw the situation, then this is the force F, that is 10 Newton, is acting in this direction, and the frictional force maximum which is acting at this point will be 0.3 into 5 into 10, and the mass of this system is 5 kg. So the common acceleration will be 10 minus 15 divided by 5. So acceleration comes out to be negative, that is less than 0. So this situation is not possible. It means the relative motion has occurred between A and B prior to the relative motion occurred between B and the ground. So in that situation, I can say that if this is the 2 kg block, the friction has reaches to the maximum value, that is 0.2 into 2 into 10. The force F is equal to 10 Newton is acting in this direction. And if I draw the free body diagram of 3 kg block, then 4 Newton is acting in this direction, and the value of the F2, if I calculate the maximum value, then this is equal to 15 Newton. It means the F2 which is acting at this point must be 4 Newton because the static friction is self-adjusting in nature. So if I calculate the acceleration of 2 kg block, that is A2, so it is equal to 10 minus 4 divided by its mass, that is 2, so it is equal to 3 meter per second square. So let's check the options. In option A, the frictional force between B and the horizontal surface is 4 Newton, that is correct. So A option is correct. In option B, the acceleration of block A is 3 meter per second square, that is the acceleration of 2 kg block, so it is also correct. The acceleration of block A is 2 meter per second square, that is wrong. The frictional force between A and B is 4 Newton. This is also correct. So the correct answer for question number 1 are option A, B and D. Let's move to question number 2. In question number 2, a uniform chain of mass M and length L is held on a smooth horizontal table such that half of the chain is hanging from the table as shown. The chain is released from rest. Choose the correct options. So at t equal to 0, the situation is given. And at the moment when the chain leaves the table, at this situation, let the situation is this. The chain is moving with velocity v at this moment at any time t. So if I calculate the speed of the chain when it leaves the table, then the work done by the normal force and the frictional force on this part is 0. So I can apply the principle of conservation of mechanical energy, as the work done by non-conservative force is 0. So initial kinetic energy is 0. Initial potential energy I can write for this hanging mass, because I have considered my reference frame of gravitational potential energy to be 0 at this horizontal level. So m by 2 into g into the center of mass of this hanging part is at a distance of L by 4, so minus L by 4. So this is the gravitational potential energy, is equal to final kinetic energy, that is half mv square, plus final potential energy, that is m into g, and the center of mass of chain length, and the center of mass of this chain of length L is at a distance of L by 2. So that is equal to into minus L by 2. So if I solve this, the value of V comes out to be under root 3 by 4 of GL. So option A is correct. Now we have to check the validity of other options. The acceleration of chain just after the release is G by 2. So just after the release, at this moment, if I calculate the acceleration, so the net unbalanced force acting on the chain is m by 2 into G, and the mass of the chain is m, so the acceleration at this moment is equal to g by 2. So option B is also correct. Let's check option C, the acceleration of chain when it leaves the table. So at this moment, the force acting on the chain is mg divided by its mass, so its acceleration is g. So option C is also correct. Now we have to check the validity of option D. The work done by gravity when the chain leaves the table is 3 by 4 of mgl. So work done by gravity is equal to minus of final potential energy of chain minus initial potential energy of chain. So this is equal to final kinetic energy minus initial kinetic energy. The final kinetic energy is half m into v square, and we have already calculated the value of v square. So that is 3 by 4 into gl, and the initial kinetic energy of chain is 0 because it is at rest. So it is equal to 3 by 8 mgl. So option D is wrong. So the correct answer for question number 2 are option A, B and C. Let's move to question number 3. In question number 3, a bob of mass m is attached at one end of a light rod of length L and rod's other end is hinge. The bob is given a minimum horizontal speed that the bob can complete a vertical circle. Then we have to check the validity of these statements. First of all, I am analyzing the situation. This is the rod and this is the bob. This is the initial situation at t equal to 0. And it is given that the minimum speed is given to the bob so that it just completes the vertical circle. So at the moment when it just completes the vertical circle, at this moment the velocity or the speed of the bob is v1. So if I consider this horizontal level as the gravitational potential energy 0 reference frame, so I can apply the principle of conservation of mechanical energy as the motion of the bob is only under the gravitational forces. So I can say that half mu square plus potential energy mg into minus L, that is the L is the length of the rod, is equal to half m v1 square plus potential energy, that is mg into L. So if I solve for v1, so v1 square is equal to u square minus 4gl. Since it is given in the question that the bob just complete the vertical circle, so for this the value of v1 is equal to 0. So the minimum value of u comes out to be 2 times under root gl. So it is given in the question we have to calculate the tension in the rod when the kinetic energy of the bob is maximum. So kinetic energy of the bob is maximum when the bob is at the bottommost position. So at this moment, if I draw the free body diagram on the bob, the mg is acting in this direction, tension T is acting in this direction. So if I write the equation, T minus mg is the net force acting towards the center, that is equal to m into u square by L. So the value of u square by L is 4g. So I can write this as 4g. So the value of T, that is maximum, and this is equal to 5 mg. So option A is correct. Let's check the validity of option B, the tension in the rod when the kinetic energy of the bob is minimum. So the kinetic energy of the bob is minimum when the bob is at the topmost position. So at that moment I can say that if mg is acting in this direction, let tension T dash is also acting in this direction. So I can say that T dash plus mg is the net force acting toward the center, and that is equal to m into v1 square by L, that is 0, because we have given the minimum speed at the bottommost position. So the value of T dash comes out to be minus mg. So we can say that tension will act on the bob in the upward direction and not in the downward direction, and the value is equal to mg. So the option B is wrong. Let's check option C. The tension in the rod when it becomes horizontal is 2 mg. So suppose this is the situation when the bob is at this position, and at this moment the speed is v. So if I check two positions, at this position and this position, if I apply the principle of conservation of mechanical energy, then I can say that 0 plus half mv square is equal to 0 kinetic energy at the topmost position plus gravitational potential energy mgl. So from here the value of v square comes out to be 2 times gl. So if I calculate the tension at this moment T2, so it is equal to T2 is equal to m into v square by l. So that is 2g. So option C is also correct. Let's check the validity of option D. Acceleration of the bob when it just becomes horizontal. So at this moment, if I see what are the forces acting on this bob, when the bob is horizontal, mg is acting in this direction and 2mg is acting in this direction. So I can say that the net acceleration at this moment is 2g whole square. That is the centripetal acceleration acting on the bob at that moment, and the tangential acceleration that is acting, that is g whole square. So if I solve this, it comes out to be under root 5 into g. So option D is also correct. So the correct answer for question number 3 are option A, C and D. Let's move to question number 4. In question number 4, a uniform rod of length 4L and mass 4m is bent into the shape as ABCDE as shown. The rod is hinged as C and can rotate freely about it in vertical plane. The rod is released from the current position at rest. Then we have to check the validity of these statements. So in option A, it is given that the angular acceleration of rod just after the release is 3g by 10L. So at this moment, if I write the torque equation at t equal to 0, then I can say that it is equal to I into alpha, and that is equal to, if I write the torque of the forces, so mg into L by 2 plus mg into L. The torque of this rod BC is 0 and the torque of the rod AB is mg into minus L by 2. So this term gets cancelled out. So the net torque is mgl and this is equal to I alpha. So first of all, I have to calculate the value of I. So I can be written as 2 times ml square by 3 plus ml square by 12 plus m into 5l square by 4. So this is the net moment of inertia. So from here I can calculate the value of alpha. So it comes out to be 3g by 10L. So option A is correct. Let's check option B. The angular speed of the rod when the rod rotates by an angle theta is equal to tan inverse half is 0. So let's check this thing. If I calculate the position of the center of mass of the given combination at t equal to 0, then I can say that xcm is equal to m into L by 2 plus m into L. The x coordinate of rod BC is 0 and m into minus L by 2 divided by 4m. So it is equal to L by 4. Similarly, if I write the YCM, then it can be written as the y coordinate of rod CD is 0. So m into minus L by 2 into 2, because the y coordinate of rod BC is also same, plus m into minus L divided by 4m. So the y coordinate comes out to be minus L by 2. So I can say that the center of mass is at this position. This is L by 2 and this is L by 4. So CM is at this position. So if I calculate this angle, if I say this angle as phi, then I can say that tan phi is equal to perpendicular, that is L by 4 divided by L by 2. So it comes out to be half. So in option B it is given that the angular speed of the rod when the rod rotates by an angle theta equal to tan inverse half. It means that when the rod is rotated by this much angle, the center of mass is shifted from this position to this position. So there is a positive loss of potential energy which is equal to gain in kinetic energy. So in that situation I can say that omega is not equal to 0. So option B is wrong. Let's check the validity of option C. If rod comes to an equilibrium position at last, then the angle made by CD with the vertical is tan inverse 2. So if I see this initial situation at t equal to 0, if this angle is phi and let this angle is alpha, then I can say that phi plus alpha is equal to pi by 2, or I can say that tan alpha is equal to cot phi, and that is equal to 2. So from here I get the value of tan inverse 2. So I can say that if the rod is rotated by an angle phi, then the center of mass is shifted from this position to this position, and it's come just below C, and at this situation only the rod comes to an equilibrium position. So at that moment, if I say the rod CD is rotated by an angle phi, the center of mass is also rotated by an angle phi. So if the rod CD is rotated by an angle phi, the other angle the rod CD makes with the vertical is alpha, and in that case alpha is equal to tan inverse 2. So option C is also correct. Let's check the validity of option D. So in option D it is given that the hinge reaction at the hinge just after the release is 4 mg. So if I check this, suppose hinge reaction at this point is AX and the hinge reaction at this point in the vertical direction is AY. So at this instant, if I calculate the acceleration of the center of mass, then in order to calculate the acceleration of center of mass, I can say that ACM is equal to alpha into the separation of the center of mass from the point C. So that is equal to root 5 L by 4. So we have already calculated the value of alpha. So if I substitute the value of alpha, so it comes out to be 3 root 5 G by 40. Then acceleration of center of mass is in this direction. So if I calculate this angle, then this angle is also phi. So I can say that AX is equal to A cos phi and AY is equal to A sin phi. We can easily calculate the value of cos phi and sin phi from this triangle. The value of cos phi is 2 by root 5 and the value of sin phi is 1 by root 5. So if I substitute the value of A and cos phi and sin phi, then this comes out to be 3g by 20 and this comes out to be 3g by 40. So if I write the equation F equal to ma in horizontal and vertical direction, then I can say that in vertical direction 4mg minus ay, that is the net force acting downward. So that is equal to 4m into ay. And in horizontal direction I can say that ax is equal to 4m into ax. So if I calculate the net hinge reaction at point C, so that is equal to A, and that is equal to under root ax square plus ay square. So if I solve this, it comes out to be mg into under root 1405 divided by 100. So on solving, it comes approximately equal to 3.7 mg. So option D is wrong. So the correct answer for question number 4 are option A and C. Let's move to question number 5. In question number 5, a semi-cylindrical massless gate pivoted through a horizontal axis passing through point O, holding against the stationary liquid of density rho as shown. The length of the cylinder is L, and we have to check the validity of these statements. So if I consider an element, suppose at a distance y of length dy, suppose this level is at y and this level is at y plus dy. So I can say that this vertical separation is dy. So the pressure at this point, since dy is very small, so the pressure at that point, pressure exerted by the liquid is rho g into y, and the force which is acting on this considered element by the liquid will be dF, and the value of dF is equal to rho gy into considered cross-sectional area. So the length of the cylinder is L. So if I consider this length as dx, this length as dx, then I can say that this is equal to L into dx. So if I consider this as my vertical line, then this force makes an angle theta with this vertical line. So the net horizontal force exerted on this element dfx is equal to df into sine theta. So if I substitute the value of df, so that is equal to rho into gy into L into dx sine theta. So if I see this diagram, we can see that dy is equal to dx sine theta, because if this angle is theta, then this angle is also theta. So from here I can say that dx sine theta is equal to dy. So I can write this as rho gl into y into dy. So the net horizontal force exerted by the liquid on the gate can be calculated as Fx integration of dfx, and the variable is y, and the y varies from r to 3r. So if I solve this, it comes out to be 4 rho r square L into g. So option A is correct answer. Let's check what is the net vertical force exerted by the liquid on the gate. So the net vertical force exerted by the liquid is equal to the buoyancy exerted by the liquid on the gate, and that is equal to weight of liquid displaced. So weight of liquid displaced is volume of liquid displaced, that is density, into pi r square by 2, that is the area, into length L. So this is the mass displaced into g, so that is equal to weight displaced. So option D is also correct. So the correct answer for question number 5 are option A and D. Let's move to question number 6. In question number 6, imagine a light planet revolving around a very massive star in a circular orbit of radius r with orbital speed v and time period t. If the gravitational force of attraction between the planet and the star is proportional to r raised to the power minus 5 by 2, then we have to check the validity of these statements. So we know that when a planet is rolling around a star, the required centripetal force is provided by the gravitational force. So the gravitational force can be written as K divided by r raised to the power 5 by 2 as per question, and this is equal to required centripetal force. So this is equal to mv square by r. So from here the value of v square comes out to be K by m into r raised to the power 3 by 2. So we can say that v square is proportional to r raised to the power minus 3 by 2. In order to calculate the time period t, so t is equal to 2 pi r divided by v. So the value of v is equal to under root k by m into 1 divided by r raised to the power 3 by 4. So I can say that t is proportional to r raised to the power 7 by 4. So if I calculate t square, so it is proportional to r raised to the power 7 by 2. So option A is also correct. So the correct answer for question number 6 are option A and D. Let's move to question number 7.